The paper, the problem with the paper is that when you train a neural network, you have a lot of data, but your data set is mostly biased because it only captures a small part of the world. And when you try your train neural network on a target domain, it probably will fail. So the natural solution is that when you have labeled data in your target dataset, you usually fine-tune the original network to work on the new target domain. But this doesn't work when you have unlabeled and limited labels. So the solution is that you should adapt your neural network to the target domain. So the paper proposes a new loss function. So the first, it has 3 terms. The first one is the common loss function for classification. So originally you have your source data, then you have your neural network, and then you have your classification loss. So now you have you add the target data, you share the parameters between the networks, and you still have the original classification loss. But this will make that your results will be overfitted by the source data. So, for example, here in this slide we have the original data, and we have 2 classes. The first one is bottle, and the other one is telephone. So our neural network performs well the classification on these images. So when we add the target data, our classifier doesn't work well because it has a different domain distribution. So here the problem is that we have discrepancy among data sets, and we need to try to fix this discrepancy. We need to make it low, and they propose two new loss functions. The first one is in the upper left of the slide, and the second one is in the upper right of the slide. So the first one is to distinguish between domains, because we already know which images correspond to which data set. So they propose a domain classifier. We can distinguish between both. So the task is to make undistinguishable between them. So they propose a confusion loss. So once you train the neural network, the domain classifier won't work because now it's mixed, but our object classifier won't work. So now the architecture of the neural network, well, we have to add the domain confusion loss and the domain classifier loss after one layer before the last one. So now this is the second. You add the second term to the loss function. Now we have another trouble because sometimes on the target data set we have limited labels. So for instance, you can have all the categories in your dataset, but you don't have too many labels for each category. So they propose another loss function. So this one, what they do first is that from the source images, they pass each image of each category to the softness layer, and they have this distribution that is basically a probability. So then they add this probability and they have the mean probability. So we have here, this slide, we can see the bottle, and here we can see the probability distribution. So this has the objective that, for instance, the bottle is closer to one mug than a keyboard. So the keyboard was penalized in this distribution. So now, well, you add the cross-entropy loss to the architecture. You pass a target image. So you compute again the softmax distribution, and you compare it with the one from the mean. So you penalize according to that distribution. Now, the last step on this architecture is you add the softmax high temperature layer and the cross-entropy loss to the architecture.
Yep. Okay, you are going very fast, so in 5 minutes explain the whole article.
Okay.
So, okay, try to explain well so all the ideas come to the people, right?
Okay.
Okay, so for example, go. So here you say that they are learning from the source the relation between different categories. Okay, so if it is bottle, we learn that the keyboard the probability should be small.
Yeah.
Okay, so how do they use this in order to penalize on the target?
Okay, so well, the thing is that you might not have the data from in the target data set. You might not have labels for the mock category.
Okay.
So, but you have data for the bubble category.
Okay.
So what you try to do is trying to compare this distribution with the result from the network. So you might not have the labels, but you will have you have the results from the original source. So you just kind of compare. Yeah. And the cross-entropy loss works at the level of the distribution. So you can see that here. Well, during the training, we have to make the most. We have the tasks to make really similar this distribution to the mean one, to this one. So this the cross-entropy loss penalizes for each category from the distribution. So it takes into account the bubble, the mouse, the chair, the laptop, and the keyboard.
Sorry, Darrell, the physical area the score of the classifier, but on the source domain.
Well, here.
This is the source domain, or
this one is well, it's like a zoom. It's like a zoom from this architecture. It's like looking at this part of the architecture. So. So yeah, it's like looking at this part. No. It's like looking at that part of the architecture. So well,
what happens if you don't have all the different categories? Some of the categories you cannot compare for description, right?
Well, the categories have to be the same.
Okay, so let's imagine that bottle you have in the target and source.
Yeah.
Okay, so you classify the target And then you classify with the source, and how do you, and when you use the softmax, the probability that's given by the source network,
Okay.
how do you use it in order to improve the plan?
Okay. So this part, the softmax, you will take it away when you stop training. So.
You force the distribution of the value to be similar to the distribution of
the resource, yeah.
Basically.
Yeah. So this one just tries to make the distribution like really, really similar, even if you don't have all the labels to the target.
Yeah, this is one. And how do you do this?
Well, the cross-entropy loss, I don't show it in the slides. So the cross-entropy is something like you go for each, I think it's for each example, for each example from the training set, and for each category, you take, this is the target C, and it's a log, it's over PC, and here is the other category. So we have this. This is the cross-entropy loss. So we try to compare two distributions. So if you have, you can see it like really fast in a mathematical way. If they are equal here in this term, I mean, if they are like 0.8 and you have 0.8, if you take the log, we will have 0. Yeah, so for each category, if they are really equal, if this one is equal to the other one, we just score 0. So that's how they compute the percentage. Okay. So do you have more questions?
It just go step by step.
Yeah, never.
Okay. Good.
So they add that this term to the loss function.
Can you explain the different terms?
Sorry?
Can you explain the different terms in the three terms? The loss is?
This one, the first one, it's the classification loss.
Okay.
So it's this time, it's this part.
Okay.
So this one, the second one, it's the loss from the domain confusion loss and the classifier loss. They don't really say how they get this term on this equation, but they add. And the next one, the soft, is this cross-entropy that I just explained. So maybe there is another doubt about the shared parameters in the architecture. So believe that when you are training backpropagation neural network, we have here the backpropagation network. So this goes like a black box, and you have your input here. And here you have your output. So the first step for training a neural network is you do a forward pass. Then the second one is to calculate the error. In this case, is the loss function, and then you backpropagate the error across the neural network. So in this case, when they say that they share parameters, they only have one neural network. They don't have two neural networks, but the training is kind of different. So they have, let's put the common stuff in the diagram. So they share the classification laws, and the domain confusion laws, and the classifier laws. So we can put here the classification laws and also the domain confusion laws. So they share this one. The only thing that they don't share is the cross-entropy laws. So what they do, it depends, the training depends on the input. So if you have images from the source, from the original source, you pass the input, you do the forward pass, then you calculate the error for these ones, and you backpropagate it. But now, let's say that it comes from the target. So you go to the target, you got the target image, then you do the forward pass, and you will calculate the error. But in this case, you additionally calculate the cross-entropy loss. And you backpropagate the error. So they only have one neural network. Now let's see the experiments. So what they have is they do two experiments, and they did also two sub-experiments. So the first one was to adapt in 3 data sets with a beam on office stuff. So the data comes from Amazon, from my webcam, from the DSLR. So they have 15, they have 31 categories. They train only using 15. And well, the results show that they overperform the baseline in all the tests. Additionally, they show that.
Can you explain the data?
Yeah. Okay. Yeah. Sorry. Here we originally have three data sets, so they have to adapt for one to the other one. So the result is that we have six tests. So for example, the first one comes from Amazon to webcam. The second one comes from Amazon and adapts to DSLR. The last one here comes from webcam and it adapts to DSLR. So here they show the average position in the test. Okay, so now
and do they compare this with the traditional fine-tuning adaptation?
No, they cannot do fine-tuning because they don't have all the labels for all the categories.
But you can just, if in the target data set they just only have, let's say, 10, and they can remove the outputs from the rest of it.
Okay. I see the point.
Can you repeat the answer?
So if in the source data set they have 15 classes, and then they have to find you to a target data set that has 10 classes, they can just remove 5 outputs that correspond to the 5 the 5 mixed classes, and then find you.
I understand that they don't have enough data to express.
Well, maybe that's the point, but if they don't compare it, so I'm sure that they can find it. The problem might be that they don't have enough data to have a good result. But in fact, what they say that is that their method is better than a simple computer. But if they don't compare it, then
It's better or it's doing when we can do that?
but what does that mean that we can do?
When, for example, the number of examples is too small.
Yeah, well, but I mean, even if you have a small set of examples, you sure can do fine tuning. Maybe the problem is that there is also
They have about the rules. I saw something that they were very, very long. Also, for some category, it is they are not able at all. So yeah, I remember that for some category, they are not able at all. For others, they are about 12 or maybe.
what this means that if they don't have samples of that category, they still have
Yeah,
the class.
yeah, they are not physically in some levels.
So they want to keep the labels, even if in the target data set there are no classes. Okay.
Yes.
But no samples.
Questo è stato sull'anno 71, ci l'hanno detto, poi la provare che ci sapevo di fare domani.
And here we see that in most of the cases, adding domain confusion for subscribers is actually better, but also just the domain confusion. That is, this is the law that we don't get, we don't understand it.
Yeah, they here, basically, they only use domain confusion. They only use this part of mixing the data sets. And the sublabel, it's the cross entropy. So they report with each one, and the last one is adding both. So, well, in this table, they have the source CNN. They also use the target CNN. They don't overperform the baseline, but using both the source and the target CNN, they do well on one transfer. Okay, so this slide shows the result of having limited labels. So they present to the network monitor class. And here in this slide, in the upper part, it shows the baseline histogram of the probabilities. And in red, it shows the score for the class monitor. As you can see in the original, it classifies the monitor as a ring finder. And in the proposed network, it classifies the monitor as monitor. So it's, they are just showing how we adapt to
The baseline is when you use the original.
yeah, this this experiment was previously presented in our paper. So when they say baseline, they are just comparing the results to the other paper. Here we have.
What would they change it to the first paper?
Sorry.
Would they change it to the first paper?
The difference. Well, because
No, there is something.
I didn't really check what they did in the first paper.
But they don't compare it with the.
No, they are just showing, because this part of the softmax, of the softmax, it's really probability distributions.
Did they mention this at the baseline algorithm in the introduction, the related words?
I don't know. No. Well, so let's go over. So they train on 15 categories. So they don't have the class monitor. It was available. But they here in this slide, what they try to show is that it is really related to the class laptop computer on the bottom. So it doesn't. I don't know if you can see the red color in this bar. So this bar corresponds to the class monitor, and it's really related to the laptop computer. They show the other 14 categories for this experiment. Okay, so the last experiment they did was that they really used data sets that were really different. Here in this slide I mentioned ImageNet and Caltech, but they also use Bing and Sun. They share 14 categories, but not there are a lot more categories than what they share. So what they try to evaluate was how well it adapts with a few labels. So they did the experiment with 0, 1, 3, and 5. This plot shows the results. And here it's the x-axis is not doesn't correspond to the number. So 14 is for 120 is for 3, and 200 is for 5. But it's really the same from the paper. So the source, they try the source of the target CNN. Well, they didn't find it, but it was also right. But mine was taken. They tried sublabels and also domain confusion loss and the sublabels. So only in one case, the source was the target. CNN was better than only the sublabels. So that's the end of the presentation.
Going back to the term where you said that about this, the term relates to the loss of confusion between domains. I think here they use the article of Trevor and Darrell.
Okay.
Inspired by the name, the data set came of Trevor and Darrell.
But
They mentioned several times that they are inspired by.
yeah, well, the architecture they got inspired by another architecture. So the original architecture was proposed by, I think, were Russians.
When they use this,
Well,
the
the shared parameters of architecture was that's not really new. So it's not a really new architecture. But when they say about Darrell, the experiments, they were inspired by Darrell in some experiments. What Darrell did in those papers was try to what happened then, it was that there were famous data sets that people tried, and their work perform well on those data sets, but they realized that when they tried on other data sets, they didn't perform well. So the cited paper, Torralba did a classifier for domains, for data sets. So they were trying to find out for which image came from which data set came from an image. So yes.
And coming with the same topic as before, I was thinking now that in fact you too can apply a fine tuning if you don't have some classes. Because you can just keep the same labels and just fine tune for the classes that you have.
The question is, if you fine tune just using some of the classes, aren't you getting worse the classification of the? Yes.
Yeah, probably, but we aren't sure about that. So maybe for the third case it's going to be okay. Because in fact when they apply the tests, do they test it on the target data set or on the source data set?
On the target.
But well, if they do that, then they are not evaluating on the classes that they don't have.
Yeah, but let's suppose.
If you have 3 classes, and then you have some regional boundaries, and then you support these. So then finally you move.
Yeah, probably. But that's exactly the reason that they are good. Because in their target data set they don't have those samples. So it's a potential.
So let's imagine that you then have the labels in the target data set. So this experiment, they show that we have the source CNN, the original source, and the original target. So here they have zero labels. It doesn't perform as well as this one, but it just performs a little bit better. So yeah, it performs better than only having those CNN. And I think you were saying a lot of fine-tuning, but here they have the original CNNs for the source and for the target.
Yeah, they train on CNN just on the target
Yeah.
from scratch.
Yeah.
Well, but that's not the same. Usually I just fine tuning on the side. So usually it's better to fine tune on the source data than to take train from scratch on small data. So it's not the same.
Yeah.
And another thing that I see strange here is that if they have 0 target labels, how do they make their model to be better on that? So they are training with zero samples.
With 0 labels in the target. They have on the source, not on the target.
So they cannot adapt it and do the target resource.
Well, anyway, it's interesting because at least it gives ideas how to apply architectures. Okay.
Yeah, well, I think that the most important idea from the paper is sharing architecture. You could have a lot of loss functions according to your data set.
Do you see do you see any application directly to the clients?
Well, on the paper they say that they explain a possible real scenario where you train a robot, runs the floor. You train something, and then you sell it, and the people use it. But they have the target data set might be their phone. So what they propose is that the user sends to you some labels, sends you some examples of labels, just a few, and you will adapt the original network from the company or from your laboratory. You adapt the original network to their home, to their needs. So we can try to use that in our program at home.
The negative picture, we do, for instance, the recipe is very good.
Yeah, and I think that for the narrative we have different kinds of pictures because we can do. So I think we will put subjects and then we can write because you are not in this way capturing the images.
I think the office data set there, but actually the difference, I think also in office data set you have the distance here monitoring all
Yeah, this is did you like it?
At the end,
yes,
so it's not pretty clear in some parts of the like establishing really well-founded framework and network. So the part of mixing domain classifier and a confusion flows, it's not quite clear. But it was good. Enjoyable.
I think we should think of how the point. Okay, so I should run. I have separate studio.
that you will be better.
I need someone else. But we can go and see.